Borrowing tolerances. This topic is not new, but perhaps it deserves a reintroduction in the context of our modern world where lots of people are using 3D printers and a lot of folks who are quasi-engineers are creating new things, and I think that they could be more successful if we use some concepts that are helping us to put assemblies together. Now, this is a little bit hard for me to organize because it's not something that I've learned in a curriculum or in a book, and believe it or not, 6 years of schooling in mechanical engineering still did not cover, they really didn't cover how to build assemblies. We go through one topic at a time, and in the real world, like at my experience in Toyota, began to dive into this. How do we handle the interactions of multiple designed parts to serve a function? But it takes some creativity and it takes a lot of observation of what we already have. So I'll give you some examples of those to start with. Well, this is an engine, and it has intake and exhaust ports that are built into an aluminum casting. This aluminum casting does not have precision and it does not have flatness. So when you need to achieve sealing under high pressure, you've got to have a flat surface where you can mate your pipe without any leakage around the sides. Before they apply this gasket, they're going to machine the surface of the aluminum, and they're essentially borrowing the precision from a tooling to achieve a perfectly flat zone here. Now we're looking at the oil dipstick zone, or the oil reservoir port, and we need to have sealing again. So flatness is one way to achieve that, but they're not counting on the precision of this injection molded plastic. Instead, they're just adding this gasket to relieve us of the requirement for a perfect flatness here. On any injection molded part, you have a feature, it's a parting line. You can kind of see it there where the two halves of the mold come together. And without any, they call this flashing. Sometimes it'll stand up and it needs to be scraped off. That's an expensive manufacturing procedure. So yes, even with the very advanced tooling, we still require post-processing if you need precision. And I don't think we need to drive our printed parts or digitally manufactured parts to be any better than such features as injection molding. Okay, now let's compare this with a machined part from cast iron. This main block is cast iron. We're looking at a motor that goes inside of a compressor for a small refrigerator or water chiller. And in here we have a rotating shaft. That rotation and that shaft must be very precise in their vertical alignment. Now, what is precise about cast iron? Well, considering that they're using sand to pour this metal in, it's not precise at all. In fact, you'll notice on any cast parts, including plastic, there are no parallel lines. You have the exterior, it will have a draw angle of 1 degree or 2 degrees or something, so they can pull it apart. And that means they don't have a place where they can clamp it and perform their finishing operations. In this case, you can find one little machined zone right here, which appears to me, if I had to guess, that they machine this zone. Nothing is attached here inside the assembly to clamp and use this surface as a datum that says this is my 0 millimeters starting plane where I'll clamp and then perform machining operations. That means they had to perform machining here and then re-clamp everything and perform it again to guarantee they have this perpendicular alignment of that hole. that the shaft goes into. So we have an asset with 3D printing. That's an asset that you can't get with many other manufacturing methods, and that is the alignment that's intrinsic to the parts when they come off of the printer. I'll go back and forth a little bit to 3D printing and industrial parts. So this is the wheel bracket, which holds the wheel, and it needs to carry a lot of load. So when we have mass pushing down here, the robot doesn't break, and it's going to hold this wheel. By the way, these designs are open source. They're found on GrabCAD and the Scuttle Robot website, and they're intended to be educational examples of every single part of design for 3D printing, such as the consideration for the print direction while we're achieving strength, etc. Okay, so right here on this shaft zone, we have to achieve a very precise hole diameter. Now, the printer itself is able to give us the alignment of perpendicularity to the vertical position of the robot. So the robot stands upright, and we can count on that 3D printer, because we're working with the larger dimensions. We can count on this hole being printed without any post-processing with a perfect alignment, but we can't count on the surface finish to be exactly precise to give us the round hole of exact diameter. So this is the only part on the robot that requires some post-processing with real tools. So in this case, we're getting a size O drill bit, which is 8.03 millimeters, so that we can drill this out. The 0.03 considers the compressibility of this plastic. When you go to drill it, it stretches just a little and it compresses back down. Here's the theory behind why that hole needs to be so precise to achieve strength. I'm drawing the printing lines. So in any given part, your hole that is perpendicular to the print lines with a shaft inside, if the shaft is not perfectly aligned with the hole size, then when you apply a force, you are only contacting a small region here. And we want that contact area to be all the way across. This type of force could cause the print to split much more easily than having it very close, snug fit. This is the exact same reason why your motorcycle helmet needs to be a very close fit to the skull, so that an impact is spread over all of this area. Okay, so we know we need a precise hole. Then we have a precise bearing on a precise shaft. Here's our next example part. In this assembly, I want to control the position of the center line of a shaft that will pass through this bearing. This is where the precision is needed. The precision is not needed here on the surface finish of all the features. So, like, we know that 3D printing has a surface finish that's not reliable with high precision. We get, here, let's go in millimeters. I mean, you've probably measured many parts on your own. 5.97, we turn it 59.6. So a fraction of a millimeter will easily deviate, and but we can achieve our goal anyway with the help of these ball bearings. The bearings have a very nice precision, and each of these bearings supporting the inner ring has an influence to push our inner ring to center. So in this case, it's all been loosely put together, but we can firm it up. This one is much more tight until it gets worn in. And ball bearings are an example of a part that's so cheap, like maybe 3 cents per ball, and the precision is out of this world. Better than you get on any machining operation. The ball can do a few different things for us. One of them is looking up close at a cross section. If you were to slice this and look at one ball in the inner and outer race, it is going to contact, first of all, at all the peaks of the 3D print's deviations. And if you tighten down the diameters, then it's going to compress them, giving you a closer contact with the nominal line that you were aiming for. Then you have the team of balls. Sometimes in my print, I'll get a whole vertical line of deviation where, in this case, you can see there may be a ridge there that deviates from my nice circle. And so on the paper, if we drew that out, let's say we had this bump here and all the balls are on the inside. Well, you have the compressibility of the plastic. You can kind of imagine it working. The balls are much harder than the plastic, and they will deform plastic that deviates. So in this case, if there's one little high point, then you will have the force of all of these balls on this side pushing against the one ball that makes contact in the moment of contact with this high point, and it will crush it. So we can basically perform machining while we're in operation, and that would be what I call the break-in period for this thing. And then we have statistics acting in our favor. You can never mind this thing. When you have something that you want to have aligned and is moving, then we're caring a lot about this contact point. Let's say when you rotate this shaft, are you going to hear a tap, tap, tap? That's called runout. If it's on the tool and the tool is wobbling, you have runout. But if you have something that is very precise, like this drill bit, we know it is straight, its diameter is near perfectly consistent, and any runout that we get is coming from the tool instead. So when you're looking at precision, the reason, let's compare these two. Every machinist knows that this is a more precise situation than this. And you can probably see if I zoom in, we're getting a wobble here. So what's going on? In the less precise tool, we're needing to control in the assembly the position of this one monolithic piece. If it is deviating by 1 millimeter in the Y direction, then the center line of the clamped item deviates by 1 millimeter as well. Whereas in this situation, if one of these pieces deviates by 1 millimeter, the circle you could draw making contact with all of them has a center line that deviates by less. And you could do all the math if you wanted to, but there's a few things going on. The contact points may adjust between these. The roundness of your tool doesn't adjust, so if that's a hard tool, I won't get into that. The point is, each of these can deviate independently, and your chances are better if you can control them as well as you can control this one piece, that your center will move less. When designers need very high precision, Here's an example. Consider this a 30,000 RPM versus the 3,000 RPM drill. Higher speeds means higher forces for any different imbalance that might take place. So the collet, you will see machinists always use this for precise machining instead of a chuck. And inside of there, you have a clamping situation that is very, very precise. So here you can see, and I'm working on, let me back up and try to tie these concepts together. The 4 things that the ball does for us is 1, provide a nominal contact between ups and downs. 2, team effort, where multiple balls achieve something together. 3, distributed tolerancing, where the positions collectively give a normal distribution and improve the position of a clamped item. And 4, we'll call it force distribution, where if you have a force applied, then that force will get spread out by the ball. Something strong is contacting the ball here, while our ball is very hard and rigid. Then wherever it is contacting let's say it's plastic, then that force is getting spread. So now this can tolerate a much larger force before it deforms if the ball's contact is spread out across the plastic. Keep in mind that the force 1 is the same as force 2 in this scenario, and that the pressure is the item that will cause deformation of the plastic. And it's the force divided by the area. So our forces are the same, but P2 is much less than P1, where this is P1 on that zone here. And P2, I won't circle it on my pretty drawing. I'll go ahead and throw in item 5, which is pretty awesome. We have selective properties. Here's just a marble, equally cheap as the ball, and this is what I can use when I'm not concerned about wet or moisture in the environment, not concerned about rusting, or I don't need to avoid an electrical contact. Now I have an electrical insulator I can use if I want to have insulation. The rigidity is somewhat selective, and we can go to the nylon if we need something non-abrasive. And something awesome about the glass is that, well, just everything. This one is much heavier. If I need lighter, I go to nylon. This ball is as hard as the steel, but it's going to make it through the TSA scanner. And you can just explore on and on with still accurate and cheap parts. Jumping back to the centering and the collet stuff, I'm working on something that sort of features characteristics of a collet / a 3-jaw chuck, and I want to see if I can clamp and center something if I have control of the input centering, and see how good of an accuracy I can get. This will be open sourced, just like all my other stuff, and if anyone wants to collaborate on it before it's finished, just contact me and I'll share the design. Okay, springy things. This was the other example that I showed in my short that got a lot of views, and so spring features are somewhat popular for designers on the sharing forums, where they're showing cool features like, now I have a spring built into my plastic component, but we don't have very good control of the rate of that spring. So let's say you do all the math, you have simulation software, and you input the ABS plastic, whatever you have. Now you know the spring rate and the stress it can tolerate, but even still, we don't have a deterministic output. I would admit compared with injection molding, your deviation of the features, the quality, the geometry, and the just internal defects, the effects of layers is going to impact this part from one to the next. Even if you change your spool of filament of the same type, you can get different features. And so this one's already wearing out. I just pulled it a little too hard, and you can see it's starting to split here. So we don't have consistency in the springs characteristics. See, on the very first trial, these slots came right back and realigned, but now that I've played with it, it's not doing that. So now I want to borrow a spring rate, but I'm also borrowing more than that when I switch to this. Okay, so it totally changes the way that the geometry clamps onto my din rail. Okay, I want the green part not to wobble like this, and the din rail is fixed. That means I need to pinch this region here very accurately. So let's rotate our view. We're gonna get basically looking towards it here in this area. Now this is the flange zone of my din rail, and the spring comes down, and you can see it like this. That pinch must be accurate. Now we're working with only about 1 millimeter, and we already know this may deviate 1/4 of a millimeter. If my metal part were 3D printed, then I could have deviations in its size, and I could have deviations in its position that are too large stacked up with this deviation to give me a consistent clamping here without a gap. You could open a whole box of these paper clips or even purchase other brands, and you will find that they are very precise in the diameter of the wire and of the flatness where the wire lays down. And these manufacturers didn't care about keeping that perfect tolerance, but since we know about their manufacturing, we know we can borrow that from them. I'll have to talk about material memory, which really doesn't exist. Okay, so we've probably experienced in life that if you have a rope or a wire and you bend it, over time it may take on a different shape after you've bended it for cycles, but this is not really what's going on. If I pull this in the elastic deformation, that means some amount I can pull this before anything permanently deforms, and it will spring back. That's kind of any material. But you can count much less on the numeric elastic coefficient of plastics, because if I pull this a little and then I raise the temperature and I cool it, do a couple of cycles, now it's going to have a brand new shape, whereas the spring steel doesn't care. Any temperature that a human can survive, this thing will not change its properties. So this is spring steel. This green component is also spring steel, and it has quite a bit of deformation it can be subjected to before it goes into plastic deformation. That is, elastic is what you get that springs back. Plastic is what you get if you push it too far. So spring steel that is fairly deterministic and consistent, you can find out the material, and you know that if I deform this only the same amount that it was deformed in its original design, that it will return as I intended, and it will not reach plastic deformation. I'm saying you don't need to know the math to get this to operate as a spring. You can just stay within the constraints of what you found before. So I can, open and close this 10,000 times and it will still close again. I talked about borrowing smoothness and toughness from the HDPE. It's a high density polyethylene for this part. This hinge I use these brackets to carry fairly heavy loads. And in this case, I have a table that gives me a pivoting action. And of course, the designs are parametric. So you can change one feature of the design without redesigning the whole component. And you can get it to attach to different things or change the dimensions. But toughness is not just an adjective, it's an actual engineering metric. Toughness is a metric that relates to impact or impulse types of loads. And so in a part like this, we could fail at this blue circular region or in the center hub. And if it was all the same material, I know that my failure location will be in the center because this area is smaller than this area. So the total force is concentrated on that pin. These are print-in-place types of models, and they're made to add one component after. I take a piece of HDPE tubing from water systems. I'll show an example. And then this goes into the part. Push it in. Even if there's defects, we just don't care about those. Since this component is printed with 3 pieces all in one, then there's a little bit of adhesion here in the gap. And the design intends for us to break this free before it's put into use. And do this the boring way, or since we have the toughness of these tubes, we should be able to smack it. And now we have that free, and it will just get smoother with use. But it's already pretty smooth. Polyethylene, or HDPE, is very cheap and very tough because it comes in these long spools for making water systems. Urethane is also very tough, and you'll often find it in pneumatic hoses. So I want smoothness and toughness. Urethane and HDPE both are very tough, but I have a test to check how much friction will I get, and you can hear it. If you rub this on something, you're gonna get this sound like that. And this one is very smooth. The matte color is a little bit of an indicator too of how that's going to rub against materials. You can also look up some of these properties online, but expect a lot of deviation in the results. What my takeaway is that ABS plastic is certainly more tough than PLA and PETG, the other very common printing materials. And HDPE also beats these two, but in many tables I can find HDPE with a larger toughness than ABS. And then we can look at friction coefficients, where static friction coefficient here, the lowest is HDPE out of the items we're comparing. I believe nylon also would be very low, nice static coefficient. Okay, this video merged many ideas and considerations, but I called it borrowing a tolerance. So here's the idea that brought me to use that term, borrowing tolerances. How much tolerance do you think you have in a golf tee that's made to be used once and thrown out? These tees are made certainly with a poor tolerance compared with this very precisely machined set of calipers. But we do know that we can rely on the tee to put a ball where the ball is supposed to go. So in this situation, I want a reliable measurement of this ball, and I don't have a true value anymore given what I was measuring. But what I can do is I can say, I want to compare this ball to the next one by contacting it in a reliable position. And I can see that the balls have the same dimension. Now, if I want to know the actual number, all I've got to do is look up the first one, or have one occasion where I was able to measure that first one accurately. We borrowed the tolerance of this assembly of the calipers to achieve repeatability in our goal. As I mentioned before, this topic I've called borrowing a tolerance really could expand on and on and on, and it's not one topic that you can really categorize as in a textbook. So I thought about what elements I brought in to demonstrate the concepts I'm sharing, and if you liked this content, here's maybe how you can help. I'd like to create more of the features that were helpful in the coming videos. So I shared useful parts to use, such as the ball bearings. I shared geometry in CAD, so the thought processes behind integrating those parts that you're pulling into your assembly and how to accommodate those down to each dimension. Material properties, so when we're wanting to borrow characteristics of a material, how do we evaluate those, measure those, and what's available out there as far as those properties? And then finished examples. So do you want to have more discussion of the parts we've designed, myself or the Scuttle organization, that are open source and you could probably try to repeat on your own? And finally, mass-produced examples where we can see some of these characteristics out in the wild, borrowing tolerances or material properties. I can draw a box around them on components that are probably familiar to you in everyday products and dive into what's the engineering behind that. I'd love to know what was helpful to you and what you'd like to see more of. So if you leave a comment, and then please use these topics, maybe mention them in your discussion, and that will help steer me into how do I put together the content that's best to help our designers all around the world.